So I'm going to put a video completing the backside of the worksheet from section 1.3 and 1.4 to give you another example of some of the things we did in class. So on the back of this worksheet are just some problems that are just like the ones from the lecture slides. So you may want to compare these to those, and having watched this solution, go back and perhaps fill in the details from the ones in the lecture slides. Okay, so the way we in class, the way we found the exact slope of a curve at a point. So that is in this case the slope of this tangent line that just touches the curve right there. The way we did that was we imagined a second point on the curve, and so we're going to label these 2 points. This one, we know the x-coordinate here is -1, and so that means the y-coordinate is just f of -1, which we could compute. And then this other point is going to be sort of a hypothetical point where we say, well, let's just draw another point that's nearby. And so nearby we'll denote -1 plus h. And again, we think of our h as being just a small amount. So that might be -1 plus 0.01 or 0.001. But the smaller h is, the closer this point is to the original point. And then, of course, the y-coordinate is f of whatever the x-coordinate is. So those are the 2 points that I would label, and then I would calculate the slope between them. I'll say, well, the slope is about, so when I say the slope here, I mean the exact slope. So the slope of this dashed line is approximately the slope between the 2 points that I've drawn. You can see those 2 points, if they're close together, it looks like they both lay on this dashed line. And so the trick is to get them close together. If you draw them far apart, then they're not going to both appear to be on this line. And that's the idea of using this h to stand for an amount that is very, very small, which will make the 2 points be very close together. So the slope between these 2 points is given by the difference quotient. And so this is what it always looks like. This is how the calculation started off in class. And so then I have to simplify this, and this is going to require a little bit of algebra. The denominator is always going to simplify. That should be minus -1, like that. So it's going to always simplify to just be h, and in fact that's how the book writes the difference quotient formula, just with an h down there altogether. This piece, f of -1 plus h, I've got to very carefully put -1 plus h in for x in the formula for f. And that'll be -1 plus h squared minus -1 plus h. You notice I'm putting parentheses around things just to be careful, make sure I really have substituted correctly. And then I'm subtracting from that f of -1, which I get by just putting -1 in for x here. So -1 squared is +1, 1 minus -1 is +2. And you can see that that's about right. I mean, you can kind of see from the graph that 2 makes sense. And so the rest of the problem is just simplifying this thing. We want to be careful. So we'll first of all multiply this guy out. This is just going to use FOIL. So I have -1 times -1 is +1. And then I'll have the outer and inner will both be -1 times h. So I'll have -2 times h altogether. And then I'll have plus an h squared. So if I use FOIL, multiplying -1 plus h times -1 plus h, I'll have this. Then I'm subtracting -1, so subtracting -1 is the same as adding 1. And then subtracting positive h is the same as just having minus h. And there's a little error check thing that you can do here, because notice that all these constants cancel out. I have a 1 plus 1 minus 2, so that adds up to 0. That has, excuse me, that has to happen in these things. If you're not able to cancel out all of the non-h terms, then you've messed something up. And we can combine the -2h and the -h to be -3h. And so at that point, the same thing happens that happened in class, which is we can factor out an h and cancel it out. Let me get rid of this line. I guess not. So I can factor out an h. I'll just write an equal sign. So I can factor out an h and cancel it, and what I'm left with is -3 plus h. And since the point is that as h gets close to 0, when this h gets close to 0, these 2 points are getting closer and closer together. And so the exact slope is going to be the limit of this thing as h goes to 0. And it's such a simple expression, it's easy to see that if h goes to 0, gets close to 0, then this thing is getting close to -3. And so I can say this goes to -3 as h goes to 0. So that's going to be my exact slope. So the slope of this dashed line is -3 exactly. All right, the practice problem 4 goes through exactly the same algebra steps, and so hopefully by writing it out carefully like that, you'll be able to follow it. But all you're going to do here is just use an x instead of -1 in the simplification we did over here. Every single step, including, you can draw the picture if you want to, but starting here, everywhere there's a -1, just put an x and see if you can do the same algebra all the way to the bottom. And what's going to happen is, in terms of x, instead of getting a -3 plus h going to -3, what's going to happen here is that your slope calculation is eventually going to be 2x plus h minus 1. And so as h goes to 0, as h gets close to 0, this is getting close to 2x minus 1. And so that's our idea of a derivative formula. The derivative formula here is 2x minus 1. In other words, on this curve, if you want to know the slope at any point on this curve, so here's the curve, any point you pick, like a -1, if you want to know the slope there, you can just plug -1 into this formula. So if you put -1 in here, you'll get -3, and that's the slope of that line. If over here you wanted to know what's the slope of the curve at that point, well, that's the point where x equals 1, and so the slope there is going to come from taking this expression and putting x equals 1. So if I do that, I'll get 2 minus 1, which is 1. And so I know that the slope here of the curve is actually equal to 1. And so I can do that for any point on the graph. I can use this formula now to calculate its slope. So the way that we can take advantage of that is that now, when we make a little table of points to plot, we can add an extra row for the slope. So not only am I going to be able to calculate the x and y coordinates, I'll be able to calculate the slope because I have this slope formula. So for example, when x is -2, the y coordinate is 4 minus -2, which is 6. And the slope formula says 2x minus 1. When x is -2, still this is -2, 2 times -2 minus 1 is -5. And so on my graph, I know that I'm going to plot the point -2, 6, so that's here. But more than that, I know that the graph is going to have a slope of -5 there. And so if it's hard on this tablet, but you could actually just put a ruler down and draw a line that's going over 1 down 5, over 1 down 5. That's what a slope of -5 would look like. So we have this visualization of not only a point on the graph, but also the shape of the graph, how steep it's changing. And we can do that for each of these points. So the y coordinate when x is -1 should be 2, so that's here. And the slope when x equals -1, that's coming from this formula. I plug that in, and then I'll just -3. That's the one we just did before, and so it's a little bit less of a slope. Pretty terrible, but it's not as steep as -5, but it's still going down. When x is 0, y is 0, but the slope is -1. So now the slope is kind of going this way. Right? When x is 1, y is 0. Oops, y is 0. And when x is 1, the slope formula when x is 1, the slope formula says 2 times 1 minus 1 is positive 1. So when x is 1, my y coordinate is 0, but my slope is now positive 1, so heading upward. and then it's easy to fill in. When x is 2, then I'll have 2 squared, 4 minus 2 is 2, and that'll be a point there. And again, the slope formula, putting 2 into this thing gives me a slope of 3. And so you start to see that it's not too surprising that it looks symmetric. We know this is a, remember, we know this is a parabola, and we know parabolas are symmetric about their center. So it's no surprise that whatever the slopes are here, the symmetric slopes, the negative versions of them are over here. So these do match up in pairs, but that's only because parabolas are symmetric and most graphs are not. So that's it. That's how we work through those. We'll continue working on them in class, but I want you to have this video available so you'd be able to look through it as you try to attack some of these problems.